Hi, my name is Darian Hirotsu, and welcome to our NEC SDN Technical Deep Dive series. In this video, we'll show you how to implement a software-defined network using NEC's ProgrammableFlow controller and Dell OpenFlow switches. As network architects and engineers, we are often required to design and deploy multi-vendor networking solutions to prevent vendor lock-in while still meeting requirements for high availability. This video is for engineers looking for details on how to implement these types of software-defined networking solutions. To illustrate how to build a software-defined network with NEC and Dell, we shall cover the following 4 steps. First, we shall illustrate the high-level integration between Dell OpenFlow switches and the NEC ProgrammableFlow controller, or PFC, to give a little bit of background. Second, we shall introduce how to design and deploy Layer 2 and Layer 3 virtual tenant networks, or VTNs, using the NEC ProgrammableFlow controller. Third, we shall cover one of the high availability features supported by the Dell and NEC integration called MCLAG, or Multi-Chassis Link Aggregation. Finally, we shall wrap up the video by illustrating a demo of a working SDN using NEC's PFC and various Dell OpenFlow switches. To provide an overview on how to build a software-defined network using NEC and Dell, we shall start by illustrating the high-level components. Using NEC and Dell, network engineers may separate the control and data plane to enable application-driven networking. This is achieved using an SDN controller provided by NEC called the ProgrammableFlow controller, or PFC. The PFC simplifies a network deployment by providing a network virtualization layer that hides the details of the physical network, as well as centralized policy management, both of which we shall discuss in further detail later in the video. Moving on to the bottom of the illustration, notice that we have a physical network leveraging OpenFlow to interface with the NEC controller. The OpenFlow network in this scenario is provided by an array of different physical Dell OpenFlow switches. Note though that this network could be extended by other OpenFlow components, such as NEC's PF1K virtual switch. Next, we shall illustrate the configurations necessary to integrate Dell switches with the NEC ProgrammableFlow controller to support OpenFlow in this fashion. Here we illustrate the OpenFlow configuration for a Dell S3048 OpenFlow capable switch. Starting with the left side of the screen, we're illustrating the OpenFlow control channel configuration. At the top of the slide, note that Dell OpenFlow switches have configurable CAM table options which can be adjusted per the specific use case. The CAM table configuration may vary by platform. We also have 2 ports, Gigabit Ethernet 1/1 and Gigabit Ethernet 1/2, each configured with a traditional VLAN, namely VLAN 3100 and 3200 respectively. These VLANs have IP addresses to ensure the Dell switch may establish the OpenFlow control channel to the NEC PFC cluster. Towards the bottom, we have the OpenFlow instance configuration. The controller IPs shown in this instance are floating IPs, or FIPS, that may failover between NEC PFCs in a cluster for high availability. Moving to the configuration on the right, we are illustrating an example OpenFlow data plane. Notice that we have example interswitch links 10 Gigabit Ethernet 1/51 and 1/52, which connect to other OpenFlow switches. These are configured with OpenFlow untagged VLAN 2 and tagged VLAN 4094, which are required by the NEC controller for topology discovery and unicast flows. We also have an example data VLAN, VLAN 10, which may be used to carry customer traffic. The port 10 Gigabit Ethernet 1/49 may connect to a server or network device that transmits this traffic. In the next slide, we shall cover the NEC PFC configuration required to integrate with the Dell switch shown here. To complete the OpenFlow configuration, this slide shows the required configuration on the NEC PFC to integrate with the previous Dell OpenFlow switch. Using the proper PFC CLI utility, we can review the PFC's floating IP, or FIP, configuration. Note that there are multiple levels of high availability in this example. As shown previously, each Dell OpenFlow switch has 2 configured sessions to the NEC PFC controller cluster. Note that only the configuration of the primary controller is shown in this figure. However, 2 PFCs are configured in this example in an HA pair. Next, we shall highlight how to verify the OpenFlow control channel between the NEC ProgrammableFlow controller and Dell OpenFlow switches. Here we're illustrating the output of a working OpenFlow control channel to the NEC ProgrammableFlow controller. Notice the CLI output from the Dell OpenFlow switch illustrates that we are leveraging OpenFlow version 1.3 and have an active or connected session to the PFC cluster on FIP 192.168.100.200. Although the second session to the PFC cluster on FIP 192.168.90.200 shows not connected, the configuration in place is correct and will transition to the connected state should the other OpenFlow control channel connection be lost. On the next slide, we'll illustrate the verification of OpenFlow on the NEC Programmable Flow controller. Here we are showing the output from the PFC CLI showing a working PFC cluster. Recall in this deployment, we have two NEC Programmable Flow controllers deployed in a cluster for high availability. In this slide, we will only be showing the CLI output from the PFC in the active state. The active state in the command output on the left indicates proper functionality of the Programmable Flow controller. Moving to the right, we are entering the PFC shell to get the details of the Programmable Flow controller configuration. After executing the show OFS info command, we see the data path ID and the IP address of our Dell S3048, which is properly established in OpenFlow control session to our PFC cluster. Next, we shall dive into NEC's network virtualization technology called virtual tenant networks. To provide some background on virtual tenant networks, VTNs are NEC's network virtualization technology. Engineers may deploy VTNs which provide an abstraction from the physical network. VTNs enable packet forwarding over an OpenFlow fabric without requiring a detailed understanding of the physical topology or complicated device-by-device configuration. VTNs also enable multi-tenancy and per-tenant policy management. VTN configurations are only deployed to the NEC Programmable Flow controller, and doing so causes the PFC to program the required flows into each relevant OpenFlow switch to realize the forwarding behavior described by the virtual tenant network. As such, as noted by the last bullet, VTN configuration and required state is distributed throughout the OpenFlow network from the centralized Programmable Flow controller. Next, we shall illustrate the VTN concept in more detail. Here is our first illustration of VTNs in action and how they provide an abstraction from the physical topology. We start the scenario by illustrating a physical OpenFlow network. Recall in our upcoming demo, we shall leverage Dell switches to produce this OpenFlow fabric. Connected to this network are a series of bare metal servers or hosts running hypervisors and virtual machines. Next, we highlight our first look at a virtual tenant network called Tenant A. This VTN allows for the customer or tenant to forward packets between the required hosts while maintaining multi-tenancy. To illustrate this multi-tenancy, the operator may now add an additional VTN, in this case Tenant B. Doing so allows the customer to send traffic between the desired hosts or servers while maintaining separation from Tenant A over the shared infrastructure. In the next series of slides, we shall highlight the components of VTNs to understand how to design and deploy Layer 2 and Layer 3 virtual tenant networks. To start the discussion on VTN components, this slide begins with a vBridge. Operators and engineers looking to ensure forwarding of Layer 2 frames within an OpenFlow network can use the vBridge to perform this task. With a vBridge, hosts that are mapped to the VTN shall be able to forward Layer 2 frames, similarly to a physical Layer 2 switch with VLANs and hosts within the same subnet. In this scenario, we start with three vBridges, VB1, VB2, and VB3. Next, we shall illustrate vExternals, which enable the mapping of external hosts into the virtual tenant network. In this slide, we illustrate the concept of the vExternal. A vExternal is like a gateway to ensure external hosts, such as servers, VMs, or network devices, are mapped to a specific virtual tenant network. There are three methods for mapping external hosts. The first is by physical interface, which is the method used for vExternal1 and vExternal2, which map to the H1 and H2 external hosts. The second is by VLAN ID, which is the method used for H3 and H4. Notice that the vExternal naming is different for these external hosts, since VLAN mapping allows for the dynamic creation of vExternals. The last method of mapping is by MAC address, which is illustrated for H5. MAC mapping also allows for the dynamic creation of vExternals as shown in the diagram. Next, we shall highlight how to connect vExternals to other VTN components using vInterfaces. Here we illustrate vInterfaces, which allow us to interconnect VTN components. vInterfaces are similar to interface names or aliases on switches or servers. They enable us to identify specific interfaces of VTN components, such as vBridges, vRouters, or vExternals. Next, we shall illustrate how to connect vInterfaces using vLinks. In this slide, we illustrate how to use vLinks to interconnect VTN components. vLinks interconnect vInterfaces much like a physical cable would for physical interfaces. Recall from our discussion on mapping techniques, we may automatically create vExternals using VLAN or MAC mapping of external hosts. Similarly, vInterfaces and vLinks are automatically created when using the VLAN mapping or MAC mapping technique, as indicated by the dotted lines in the diagram. In the next slide, we shall highlight how to create L3 VTNs using vRouters, our last VTN component. Now we shall illustrate how to forward packets between different subnets. Recall that using vBridges, we can create virtual networks that forward packets based on layer 2 MAC addresses. To forward packets between different subnets, we need to introduce the vRouter component. In this example, H1 and H2 resided in a different subnet than H3 and H4. By introducing the vRouter to connect to VB1 and VB2, our example VTN may now forward packets between different subnets. Also, note that the vRouter is a logical component that is not bound to any physical forwarding element. The configuration and forwarding state described by the vRouter is distributed throughout the physical network. In the next slide, we shall change gears and illustrate how to enforce policy in virtual tenant networks. Here we shall detail how to centrally enforce policy within a VTN. Suppose within the virtual network we want to prevent VM1 from sending packets to VM2 and VM3. To enforce this policy, we shall use flow filters and flow lists, which are mechanisms to centrally enforce policy from the NEC Programmable Flow Controller. Flow lists are similar to ACLs and allow operators and engineers to create matching conditions based on L2 through L4 header information. Flow lists are used to create flow filters which may be applied to VTNs, vBridges, or vInterfaces within the virtual network. As terminating actions for flow filters, we shall use pass to allow traffic to be forwarded, drop to silently drop packets, or redirect to forward packets to an alternate destination, such as a firewall or virtualized network function. Going back to our example scenario in which we want to prevent VM1 from sending traffic to VM2 and VM3, we shall first create a flow list that matches the source address of our VM1. Next, we shall create a flow filter that references our flow list and is applied to the outbound interface of the vRouter facing VM2 and VM3. By applying this policy to the virtual network, the policy shall be enforced regardless of the location of VM1, VM2, and VM3 in the physical network. In the next series of slides, we shall shift gears and illustrate multi-chassis link aggregation, which is a high availability feature available when building SDNs using Dell and NEC. In this slide, we introduce the basic concept of MC-lag, or multi-chassis link aggregation. Recall that normally lag interfaces connect the same devices, such as network switches, to servers. In that type of scenario, the network switch may be a single point of failure for the connected server. MC-lag, on the other hand, provides additional redundancy by allowing traditional hosts to home to multiple network devices using a single lag interface. Using MC-lag, as shown in this example, a device such as a layer 2 switch can home to multiple switches using a single lag interface. Traffic sent from a source, such as the host shown in this slide, can be hashed across the different ports in the MC-lag. In the next slide, we shall illustrate how MC-lag is deployed using NEC's Programmable Flow Controller. Now we shall detail how MC-lag is used with NEC's PFC. As shown at the top of the slide, VTNs and their components are deployed normally, as illustrated from our previous examples highlighting VTN design. In the top diagram, we have a vExternal that faces a traditional department LAN consisting of various devices. As shown at the bottom of the slide, the vExternal may use interface or VLAN mapping for the MC-lag port. The MC-lag terminates between Dell OpenFlow switches and a traditional layer 2 switch. Note that one requirement for MC-lag is the usage of stack links to connect the edge OpenFlow switches that terminate the MC-lag. This is similar to how most traditional networking vendors deploy MC-lag as well. In the next slides, we shall detail how to configure MC-lag on the NEC Programmable Flow Controller. At the top of this slide, we highlight the steps to configure an MC-lag on NEC's Programmable Flow Controller. Note that the steps are the same regardless of the underlying OpenFlow switch in use. To start, we have to create what NEC refers to as a trunk port or trunk port group. Next, we add OpenFlow switches to the created trunk port group that will terminate the MC-lag port. The next step is to configure the stack link properties. As noted by the bullets on the slide, there are two deployment modes for stack links. The demo and the upcoming example shall use shared stack links, which allow for a single set of stack links for any amount of MC-lag interfaces terminating on the OpenFlow switches. Next, we shall configure link down relay, which prevents black holing of traffic during various link failure conditions. Finally, we have to configure the mapping technique for the vExternals. In the next series of slides, we shall highlight examples of these various configurations. This slide starts by showing how to configure MC-lag, including the trunk port group, the associated shared stack links, the MC-lag trunk port, and lastly the vExternal mapping. The top of the slide starts by configuring the trunk port group to add the associated member OpenFlow switches to the MC-lag. Notice that OpenFlow switches are identified by the datapath ID. Recall in previous slides we illustrated how to retrieve the datapath ID via various command output. Also illustrated is the configuration for the shared stack links, which are required to enable MC-lag between the two OpenFlow switches. With the configuration shown, east port TE1/19 on OFS1 must connect to west port TE0/35 on OFS2. Also, west port TE1/20 on OFS1 must connect to east port TE0/34 on OFS2. Next, we have to configure the ports that face the host external to the OpenFlow network as a trunk port. In this scenario, the ports that make up this MC-lag are TE1/23 on OFS1 and TE1/26 on OFS2. These ports face an external host, such as a layer 2 switch or a server. After configuring this MC-lag trunk port, we need to map external hosts to the VTN. In this scenario, we are illustrating how to reference our newly created MC-lag trunk port called MC-lag1 using the interface mapping technique to a vExternal called MC-lag. In the next slide, we illustrate how to leverage link-down relay to augment the MC-lag configuration. Here we show how to augment the MC-lag configuration using link-down relay. Link-down relay prevents black holing of traffic in scenarios where an OpenFlow switch loses all connections to the OpenFlow network. In this scenario, suppose TE1/45 and TE1/46 connect one OpenFlow switch in the network to the rest of the OpenFlow network. Should TE1/45 and TE1/46 fail, an external host connected via MC-lag may unknowingly forward traffic via TE1/23, causing a traffic black hole. Link-down relay allows the operator or engineer to monitor specific ports. If the monitored ports fail, the link-down relay feature disables the action port, as shown in the configuration, which prevents the traffic black hole. Next, we shall highlight a demo illustrating a working software-defined network using NEC's PFC and Dell OpenFlow switches. In this demo, we are highlighting the various steps to build a software-defined network using NEC and Dell. To introduce the environment, off to the left, we have two hosts running ping tests to each other, showing our functional SDN. Note that host T3 at the top of the screen is connected via MC-lag to the OpenFlow network, which we shall highlight later in the demo. Next, we shall show the details on how to build the OpenFlow network itself. Starting with the OpenFlow switches, moving to the bottom right corner, we have a terminal connected to a Dell OpenFlow switch. First, we will show the switch TCAM configuration, which is adjustable for the use case to account for the desired amount of flows per table. Next, we shall illustrate how to build the OpenFlow control channel, starting with the configuration of ports GIGI1/1 and GIGI1/2. These ports perform traditional networking to establish the control channel to the NEC PFC. Next, we are showing the configuration of VLANs 3100 and 3200, which have IP addresses to source the OpenFlow control packets. Lastly, we are showing the OpenFlow control channel configuration itself. In this demo, we are connecting to multiple floating IP addresses on a PFC cluster for additional redundancy. Now we shall illustrate the OpenFlow data plane. Port 10GIGI1/49, as shown here, connects to a server running a virtual machine, sourcing the ping test in the bottom left. Next, the two ports 10GIGI1/51 and 1/52 connect to the rest of the OpenFlow network. Lastly, untagged VLAN 2 and tagged VLAN 4094, as shown here, are required for interswitch links by the NEC controller for topology discovery and unicast forwarding. Finally, we are showing VLAN 20, which is used in this demo for customer traffic via one of our ping tests, shown on the left. Continuing our demo, we will illustrate the PFC cluster configuration required to support OpenFlow control sessions. Using the command shown, we are highlighting the configuration on the active PFC for the demo. However, note that there is a second PFC in standby for high availability. In the output, we see the floating IP addresses, which the OpenFlow switches connect to for the OpenFlow control channels. Moving back to the OpenFlow switch, we can verify the OpenFlow control session using the command shown. Notice that controller 2 is in the connected state, indicating we failed over to the backup control session to the active member of the PFC cluster. Now, to verify the PFC, we can run the PFC show cluster status command. Note that we see our PFC in the active state, indicating a working PFC cluster. Next, we shall enter the PFC shell and run the show OFS info command. Doing so allows us to view the OpenFlow control sessions in the connected state, indicating functional OpenFlow control sessions. Note that we may use the datapath ID to correlate a control session to a particular OpenFlow switch as shown here. Next in our demo, we shall transition to cover VTN design. To continue the demo, we shall illustrate the details of VTN design. First, we shall illustrate the VTN topology as shown by the web GUI of the PFC cluster from a browser. Also, to illustrate how to debug flows within the virtual network, we are highlighting a particular flow on the web GUI interface. Going back to the active PFC, we shall now highlight the configuration of a VTN via CLI. Note that we are now seeing the configuration in two forms. The first is via CLI in the center of the demo, and the second is via the web GUI to the upper right. The VTN in question has multiple components. First, we have a vRouter to interconnect hosts in different subnets. This vRouter connects to vBridges using vLinks and vInterfaces. And also, we have vExternals using both the VLAN mapping and interface mapping techniques. The MCLAG vExternal in particular uses interface mapping. Next, we will highlight the MCLAG configuration from the PFC that was explained earlier in the video. In this portion of the demo, we shall highlight the high availability benefits using MCLAG. To the upper right of the screen, we shall bring up terminals to the two OpenFlow switches that terminate the MCLAG. The trunk port called MCLAG in the CLI configuration illustrates the physical ports that make up this multi-chassis link aggregation. Starting with OFS 1, we shall disable TE1/23. In doing so, note that no traffic is lost from our ping test as a result of this failure scenario. Now, after re-enabling the port, we can move on to OFS 2. Again, OFS 2 also terminates a port in this MCLAG. From OFS 2, when we then disable TE0/26 as noted by our MCLAG configuration, again, after failing the port, we see no traffic loss as a result from our ping test indicating a working MCLAG deployment. Moving to the final portion of this demo, we shall illustrate how to deploy policy within a virtual tenant network or VTN. After re-enabling the MCLAG interface on OFS 2, moving back to the center of the screen, we shall illustrate a flow filter and flow list configuration, which together enforce policies in the virtual network. Notice in the configuration of the PFC, we have a pre-configured flow list which matches the source IP address of T3, the host running the ping test in the upper left. Next, we illustrate the steps to create a flow filter applied in the outbound direction on the vRouter facing VM3 in the lower left corner. We start by navigating to the vRouter interface in question via the CLI. Then we create a specific entry in the flow filter which uses sequence number 10. Next, our flow filter shall reference the flow list called block T3 shown previously to match the specific packets of our choice. Lastly, we use the terminating action drop to silently drop the matching packets. Note that after completing these steps and by committing the configuration, the ping test then halts. This shows we can centrally add network policies to the virtual network as required. Now we can also remove this flow filter, which will allow traffic to resume. Note that this is just one simple way to highlight policy enforcement within a virtual tenant network. This concludes our demo, illustrating the various steps on how to build a software-defined network with NEC and Dell components. In this video, we illustrated how to build a software-defined network with NEC and Dell in 4 steps. First, we showed the high-level integration between Dell OpenFlow switches and the NEC ProgrammableFlow Controller, or PSC. Second, we introduced how to design and deploy Layer 2 and Layer 3 virtual tenant networks, or VTNs, using NEC's PFC. Third, we covered some of the high availability features supported by the Dell and NEC integration, namely MCLAG, or multi-chassis link aggregation. Finally, we concluded by illustrating a demo of an SDN using NEC's PFC and Dell OpenFlow switches.